In the late 1800s, factories across the industrial world unleashed mechanical titans that dwarfed the men who operated them. Fully assembled, these towering structures stood stories tall and weighed hundreds of tons, capable of shaping molten iron with a precision that seemed impossible for their size. When they struck, the impact detonated against the anvil with such force that men standing nearby could feel their teeth rattle and their vision blur. This is the story of the steam hammer giants, machines that walk the razor's edge between creation and destruction with every calculated blow. Now that we've seen how dangerous a steam hammer could be, let's find out how and why it was invented. In November of 1839, shipbuilders and engine makers were requesting parts so large that traditional forging methods couldn't keep up. One specific order proved nearly impossible. Zambard Kingdom Brunel, an English civil engineer and mechanical engineer who's considered one of the most ingenious and prolific figures in engineering history, required a new paddle shaft about 30 inches across for his new transatlantic steamship, the SS Great Britain. The problem was that this was much larger than any forges could handle at the time. Enter James Naismith, a blunt Scottish engineer who accepted the challenge and responded with a practical design. He sketched a simple solution. Suspend a steam cylinder above an anvil, attach the hammer block to the piston, then use steam to lift it and release it straight down. The goal was a direct controlled impact delivered vertically rather than something that swung like an arm. Engineers would later compare it to a steam engine that hung from its cylinder, built to drive motion straight up and down while lacking rotary motion. Across the channel, Francois Burden and the Schneider Company at Le Creusot faced the same need and built the first working version. There's been some ongoing dispute here. Burden built the first actual working machine, but supposedly Naismith claimed it was built from a copy of his design. Like they always say, the more things change, the more they stay the same. Anyhow, that machine weighed about 2,500 kilograms, or over 5,500 pounds, proving the concept was workable beyond paper drawings. Years later, the largest hammer frames rose as tall, open A-shaped structures of iron, and observers compared their outlines to the Eiffel Tower. It was not meant to be an imitation, but rather a celebration of scale and engineering. It was ironwork built large enough to serve as a landmark. This is the type of industrial design that represents the peak of human ingenuity and ambition. The workers described the massive steam hammer as a controlled power that could do whatever the operator at the valve required. In 1878, visitors at Le Creusot saw the steam hammer so large that it sat on an anvil block weighing about 750 tons. 750 tons. And here's the remarkable part. The workers said it could strike so softly that it could cork a bottle without breaking it in one moment, then instantly crush a glowing ingot the next, as if it were a piece of soft clay. It was a delicate balance that depended on the mill's rhythm and its needs. Its needs. The crew moved hot iron into place with tongs and hooks, and each step relied on a lift, a pause, and the drop, all landing exactly when expected. It was the kind of teamwork that only comes from years spent side by side. Think of a football team that's played together so long each player just knows where his teammates will be almost without looking. It's a kind of instinct that can't be taught. That's how these crews moved hot metal in perfect rhythm, trusting each other's timing and reactions. The work the mills produced was not small. It formed a heavy backbone of industry, giant shafts for engines, massive forgings for ships, and parts for armor and guns. Those demands were why the hammer was used so heavily and why failure was not an option. The problem was that the hammer relied entirely on steam pressure and signals. If a man was half a beat late, if the work sat crooked, or if a tool slipped by accident, the gentle tap of the giant hammer, well, that reputation ended and raw force took over. Some of these mills handled ingots up to 120 tons, and when weight like that shifts under a blow, it could jump twist, or even throw off shards. One clean strike could produce a perfect part, but on the flip side, the next could send sharp metal flying into the air without warning. That's why experienced crews had such respect for the hammer's power. They knew it could be gentle when it needed to be, but only if everything was just right. The moment that care slipped, its true strength showed, and not always in a way that anyone wanted. Contrary to what you might believe, the hammer strike itself was not always the immediate danger. In a lot of shops, it was the actual walk to reach the anvil. In 1915, one factory witness wrote that the steam hammer block was only a few inches above the floor, and at the worst, risk was lowered to the ground. Sparks and metal splinters always shot outward with the aim of a gun, and the danger zone stayed within about 2 feet of the ground. So to work in that space, men protected themselves as if they were entering a war zone. Shinglers wore heavy iron jack boots up past the knee along with an iron veil over their faces, because the floor level was where injuries happened most of the time. 5. But then again, there are plenty of photos and video footage showing the complete opposite, with workers wearing basically no protection at all. Protection didn't solve the larger problem of footing. The hardest part of the job was the run from the furnace to the hammer and back again. The scalding hot loads couldn't be set down, not even for a quick second. If the cart hit a stray piece of metal or a ridge in the floor, it could tip. And if a man slipped once, the load could slide off and rain down on top of them. In one horrific case, a young man slipped on the floor while pulling a large glowing pile toward the hammer. The barrel tipped and the mass slid onto his stomach. The men pulled it off quickly, but he died a day or two later. And the worst part was how the men were paid for this work. They were paid by the ton, not by the hour, so the more metal that they finished, the more they earned. Naturally, that's a kind of system that encouraged the men to work faster regardless of how dangerous it was. And as we all know by now, that's always when accidents happen. But it just gets worse, because that's not the only danger that the men working around steam hammers faced. At the turn of the 20th century, the largest forging works operated like indoor rail yards, with cranes moving along overhead beams and giant hooks swinging above their heads. A steam hammer might have been a centerpiece, but the cranes and the chains fed it. They were responsible for carrying the molten steel and iron from the furnace to the anvil in slow creaking arcs. Every lift depended on gravity and angles. The rigging took a beating from the shock, the heat, and the dirt. Sometimes a link looked fine, but then suddenly it stretched, broke, and gave out. And when a chain started to strain, crews only had mere seconds to react. They moved quickly. They called out warnings and tried to keep the load landing where it should, because a falling forging did not bounce. It crushed. Could you imagine standing there minding your business but also getting lost in thought, taking your eye off the prize when suddenly a huge stream of molten hot lava lands either right next to you or worse, right on top of you? It makes you think about how people in cushy office jobs today complain about having a tough day at work. Perspective is everything, if you really think about it. So in the United States, builders continued pushing for larger blows, and Bethlehem's great steam hammer was said to deliver 125-ton strikes. It's hard to wrap your mind around that kind of power. To deliver a level of force at that magnitude meant that the parts were enormous, and moving them safely mattered just as much as shaping them. But as life teaches us, not everything lasts. Bethlehem Steel built a near twin of the Le Creusot-style hammer in 1891, then tore it down in 1902. A fast rise and a hard end that showed how brutal the scale race could be. By 1902, some American mills had already learned that the most dangerous failure was not always the ram, but the tooling beneath it. A die might endure thousands of blows, repeated heat cycles, and constant grit, which would cause a small little fracture to spread through the steel. When a shop was behind schedule, worn dies sometimes stayed in service longer than they should have. The difficulty was judging a surface that looked strong while stress was still building inside of it. The men would listen for any changes in tone and watched for movement in the work. They had to be aware that the next strike could be the last one that split the die, so when a die burst, the hammer continued doing what hammers do. It kept driving down and the trapped energy had to escape, and it could throw sharp fragments across the floor, turning the area next to the anvil into a sudden hazard zone. Men rushed behind posts or raised heavy tongs as protection, but the fragments traveled faster than any reaction. Some of the largest steam hammers ran for 52 years before retirement. That long of a service life meant wear and tear was always accumulating in the background. A crack could come from flawed steel, poor maintenance, or chance, and the exact cause was never clear. All it took was one more clean hit to send shrapnel flying. Now that we understand how crucial it was to maintain the equipment in the factory, let's turn our attention to another part of the story that you might not expect. The real heart of the hammer's danger wasn't just in its iron or steam. It was in the hands and the judgment of the person who was running it. Every single strike depended on attention, skill, and split-second choices. We must not forget the human element in all of this. In the late 1880s, some giant hammers were controlled from a platform built into one leg of the frame, positioned high beside the moving work. On machines like the Great Hammer at Le Creusot, the legs stood over 30 feet tall, and the operator watched from that height as the men moved below. Felt the machine's tempo and read the crew's hand signals through clouds of smoke and sparks. Steam pressure could average around 71 psi, and that unseen force meant the hammer could lift again as soon as he opened the valve. Most of the time, errors didn't look dramatic. A blow might land slightly off-center. A workpiece might roll over instead of settling. A worker's tired hands could lose their grip on the tongs, causing them to slip or twist. The problem, as you might expect, is that in a shop that loud, even the loudest shouted warning might never reach the operator's platform. The outcome depended entirely on the operator's experience. With the same lever, a skilled operator could soften a strike, slow the cycle, or hold the ram high long enough for a man's hands to clear. That's why experienced hammermen treated the job with such respect. Control depended on human timing, and, as we know, men are prone to mistakes. By March 1918, some American factories were forging 14-inch shells under steam hammers, filling war orders that left little room for bruised hands or sore backs. The jobs arrived hot, heavy, and fast, and crews had to match their pace to keep production moving. Even off the clock, these hammer crews were recognizable around the town. Many of them looked long and thin with pale faces and dark rings under the eyes. By the end of a shift, soot covered them, and some wore it like a badge of honor. Keeping perfect time under constant heat, noise, and pressure was difficult. Pride and willpower can only carry a man so far. Every man's got a breaking point. When factory owners pushed for faster production, the small mistakes started to add up. It might be a quick step into a tight space, just one more lift, or a die that should have been checked again. A scary moment could come from many causes. A foreman pushing a crew short a man, or a worker trying to prove he could keep up. The typical bravado that we men hang our hats on. And unfortunately, these kind of mistakes aren't just history. They still happen even in modern forges. For example, in 2012 at Carlton Forge Works in Paramount, California, a worker was operating an 800-ton hydraulic drop hammer during a forging job. A length of titanium pipe was under the tooling when the force came down and something in the setup failed. A section of the pipe sheared off and became a projectile. It struck the worker and he died instantly, showing that even work that appears contained can become flying steel in an instant. From what could be observed afterward, the exact cause was not clear. It may have involved how the pipe was held, the tooling choice, shift in alignment, or failure under repeated heavy use. A shop can run for years without that result until one strike finds the weak point. This is why experienced forging crews watch the setup as closely as the hammer face. They understood the danger was not only when it came straight down, but what could slip, break free, and travel sideways with the force of the strike. One last hidden danger around steam hammers, and as you might have guessed, it's right in the name of the monster itself. In 1850, a typical prime mover was often rated at around 30 pounds of steam pressure per square inch. Over the following decades, many shops pushed that closer to 80. What did that mean? Well, higher pressure meant more work, faster speeds, and higher profits. But it also increased the risk in pipes, joints, and valves. In many places, there was no single rule book, and the plant managers often relied on experience to determine what was acceptable. A steam system held large amounts of unseen force. If a valve stuck, a gasket failed, or a pipe cracked, pressurized steam could escape instantly. It could cause serious burns in seconds, make it hard to breathe, and quickly fill the shop with thick steam, hiding other dangers from view. In a loud forge, it could take several seconds or even longer to even recognize the sound and understand what was happening. In others, maintenance was delayed because it was too expensive. This was common across all industries and time periods. Profit over safety. Every single time. People started to see the hammer as more than just a tool. It quite literally became a landmark in the shop. In 1877, the great hammer at Le Creusot rose inside its iron frame, tall enough to resemble an indoor tower. The comparison to the Eiffel Tower's outline made the ironwork feel like a monument as much as a machine. The scale extended beyond the hammer itself. 4 swan neck cranes moved iron and steel into place, and 6 Bessemer converters fed the complex with steel as if the hammer depended on an entire system operating around it. Under the hammer, the foundation was built to absorb punishment. Heavy blocks, timber beds, and deep masonry were meant to take the shock, but vibrations still traveled up wooden posts and beams. In Bethlehem and mills like it, the hammer was the factory's racehorse, always pushed to go faster as demands grew. Each new ship or engine was another lap, and the owners kept investing in stronger hammers to finish the job before time ran out. But all that progress came with a price. The same hammer that filled workers with pride also kept them grinding through endless noise, heat, and stress day after day. Eventually, the famous Le Creusot steam hammer was retired after decades of work in 1930, and the reason was simple to say, but hard to accept. New machines were taking their place in the form of hydraulic and mechanical presses. These machines could apply a more consistent force while reducing the hidden safety flaws in forging. The Le Creusot hammer's foundation reached bedrock about 11 meters down. It was built to withstand shock, which tells you how much violence the builders expected. The building had to be anchored that deep just to survive the work. What chance did a man's body really have on the floor above it? And so this steam hammer became a symbol instead of a tool, a monument to the age when iron ruled and men measured themselves against it. In 1969, it was taken apart and reassembled in the town square. And in 1981, ASMA designated it a historic landmark. It left behind pride, wages, scars, and a warning that power indoors always asks for payment, even when the bill comes later.